So this first question is, first of all, using probabilities. So I'm choosing someone from random from the table, and I've got 1,280 that have taken part in the survey altogether. So the first one is that they prefer a tablet. So looking at tablet, that's this section here. So the total that prefer a tablet is 560 out of the total in the whole group. So for the first part, A part 1, then it would be 560 out of 1,280, and I need to simplify that, which is 7 over 16. Then for the second part of the question, it's an 11 to 13-year-old, so we're only interested in this category here, and prefers a mobile phone. So the mobile phone section is this part here. So our answer is 72. There's 72 people that are both this age and preferring a mobile phone out of this part here. So 72 out of 1,280. And again, we should simplify that down, 9 over 160. And you could write the decimal as well. Part 3 is then asking that they prefer a laptop given that they are 17 to 18 years old. So the important part of this is given. Okay, as soon as you see given, you know that the denominator, this number here, is no longer 1,280. It's now that they are 17 to 18 years old. So it's going to be out of 17 to 18 years old, which is 348. So it's out of 348. I'm only choosing from people that are 17 to 18, and I wanted the probability that they preferred a laptop. So a laptop for that age group is 153. So 153 out of 348, which simplifies to 51 out of 116. And then the last one is prefers a tablet or is 14 to 16. So if they prefer a tablet or 14 to 16, then I can add them together, but I also need to realise that I'm going to have counted one of them twice. And that's the people that are both 14 to 16 and the people that prefer a tablet. So I've ended up counting this 224 twice. So if I'm going to do the total of people preferring a tablet, which is 560, and I'm adding to that the people that prefer, or the people of that age range, which is 512, but I need to remember to subtract the people that are in both sections, because otherwise they'll have been counted twice. So that gives me 848. So it's 848 out of 1,280. And that simplifies to 53 over 80. So the important part there was remembering to do that subtraction at the end. So now that we've finished the probability, we're going to move on and start looking at a chi-squared test for independence. So a test for independence is a two-way table test. So it's a chi-squared two-way on the GDC. You're told what the critical value and the significance level is. And to start off with, we're writing the null and the alternative hypothesis. So the null hypothesis for this one is always independent, and the alternative hypothesis is always dependent. So in this one, it's the age and the preferred device. So the null hypothesis is that age and device, or preferred device, you should write this out in more full, are independent. And then the alternative hypothesis is that age and device are dependent, so they are impacted by each other. Okay, so the key word there is independent and then dependent. And then part C is to write down the degrees of freedom. So to find the degrees of freedom, it's the number of rows. So I have 3 here. subtract 1, so that would be 2. And then it's the number of columns, subtract 1, which is again 2. And I times those together. So I have 4 for my degrees of freedom. And then for the last part, for part D, I'm finding the chi-squared statistic. So to do that, I'm going to be going to my GDC, and first of all opening a calculation page. And I now need to transfer my data to a matrix in my GDC. So I'm going to do Menu, Matrix and Vector, Create a Matrix. So this is where I'm going to put my table of information. So ignoring the totals, just the data, it's 3 by 3. So the first one is 143, then 205, and then 72. And then looking at the next column, which is the 14 to 16, it's 160, 224, and 128. And looking at the last column, 153, 131, and 64. And I need to store that information into my GDC, so Control and Store, and I'm going to call that A. So every time I type A, it comes up. Now I can do my chi-squared two-way table. So I do Menu, Statistics, Stats Tests, and it's a chi-squared two-way table. And then I put the letter that I called the previous matrix or the table of data. And then here we've got the chi-squared value. So when I'm writing it into my exam paper, I need to make sure I use 3 significant figures. So if I'm cutting it off here, then the 2 would keep the 3 a 3, so it's 23.3. So 23.3 for my chi-squared statistic. And then I'm asked to find my p-value. So the p-value can be found on here. So the p-value is 0.000109. And then lastly, I need to make a conclusion as to which hypothesis I'm going to take. So if we imagine what this looks like, we have our chi-squared distribution, and your p-value, you're told, is 1. So our p-value is telling us the area there, which is 1%, and that gives us our critical value. And our critical value, they told us, is 13.277. Now my values that I found are a chi-squared value of 23.3. So 23.3 is somewhere over here. And my p-value is 0.01%. So it's very, very small. So somewhere down here, okay? Since the critical value is the critical bit that tells me whether I take the initial hypothesis or the alternative hypothesis, we can therefore see that we are definitely in the alternative hypothesis area, and therefore we should be taking the alternative hypothesis. So we are rejecting the null and accepting the alternative hypothesis, okay? And you can either draw that diagram or you compare the values. So you can compare that your critical value is significantly less than your chi-squared statistic, and you can compare that your p-value is less than the significance level. So either of those ways of showing the answer would be absolutely fine.